Welcome to this session on CCNA tutorial, Network Access. This video is aligned with Cisco's official CCNA 200-301 exam blueprint and is designed to guide you step-by-step towards certification success. Section 2.1, VLAN Configuration and Verification. This section takes us into network access, where the focus shifts to how devices actually connect to the network and how traffic is logically separated at Layer 2. We start with VLAN fundamentals, defining what VLANs are, why they're used, and their key characteristics. We also cover default VLANs and VLAN ranges, explain how VLANs are created, named, and deleted, and look at how VLAN information is stored on a switch, including the role of the VLAN database and the impact of VTP. Next, we move into VLAN port membership, where we focus on access ports for both data and voice traffic and how switch ports are assigned to the correct VLANs. Finally, we introduce inter-VLAN connectivity, using a router with multiple interfaces to show how devices in different VLANs can communicate by routing traffic through separate physical connections. A VLAN is a logical way to segment a network at Layer 2. Even though devices may be connected to the same physical switch, VLANs allow the switch to be divided into multiple broadcast domains. This means broadcast traffic is limited to devices within the same VLAN, which reduces unnecessary traffic and improves overall performance. VLANs also improve security by isolating users or services without requiring separate physical infrastructure. Typically, each VLAN maps to its own IP subnet, which becomes important later when we need communication between VLANs. Cisco switches store VLAN information locally in a file called VLAN.dat, which allows VLANs to persist across reloads. When VLANs are created or deleted, the switch updates this database automatically, and it's separate from the running configuration. VTP can also affect how this database is updated or synchronized across switches, and that's what we'll look at next. VTP defines how VLAN information is managed and shared. In server mode, switches can create, modify, and delete VLANs, and those changes are propagated to other switches. Client mode switches can't make VLAN changes themselves. Instead, they learn VLAN information from servers and store it locally in the VLAN database. In transparent mode, VLANs are kept local to the switch. With VTP version 1 and 2, transparent switches still forward VTP advertisements, while in version 3, they no longer forward them. VTP version 3 also introduces off mode, which completely disables VTP and adds support for extended VLANs along with improved authentication. The VTP mode command defines how a switch participates in VTP, including whether it can create, learn, forward, or ignore VLAN updates. The VTP domain command sets the domain that the switch belongs to, which determines which other switches it can exchange VLAN information with. In this example, the switch is currently operating in VTP client mode, which means it learns VLAN information from the network and applies any updates it receives. We need to verify its current VTP mode, then change it to transparent to prevent VTP updates from overwriting local VLANs. We first use Show VTP Status to confirm the current mode. To prevent remote VLAN changes from affecting the switch, we change the mode to transparent using VTP Mode Transparent command. This keeps all VLAN changes local to the switch. Finally, we verify the configuration again to confirm that the switch is now operating in VTP transparent mode. VLAN IDs are grouped into different types. Normal range VLANs are fully supported and commonly used. Extended range VLANs are typically used in larger networks and behave differently depending on the VTP version and mode. Reserved VLANs, including VLAN 1 and VLANs 1002 through 1005, exist for legacy technologies and cannot be removed. Understanding these categories helps explain why some VLANs propagate and others do not. In this example, we want to understand how VLANs are categorized on the switch. First, we verify the VLANs configured on the switch. By displaying the VLAN table, we can identify which VLANs fall into the reserved range, which are normal range VLANs, and which VLANs are in the extended range. This gives us a clear classification based on VLAN IDs. Next, we check the VTP status to understand how those VLANs behave. The output confirms the VTP version and operating mode. In this case, the switch is running VTP version 2 in transparent mode, which means extended range VLANs are allowed locally but are not propagated to other switches. Finally, we verify where VLAN information is stored by checking the flash directory. The presence of the VLAN.dat file confirms that normal range VLANs are stored in the VLAN database, while extended range VLANs are not written there and instead exist only in the running configuration. Creating a VLAN starts in global configuration mode. A VLAN is created by using the keyword VLAN followed by a VLAN number. Once created, the VLAN exists logically on the switch. A descriptive name can then be assigned to make administration easier. At this stage, the VLAN does not affect traffic until ports are assigned to it. In this scenario, a new VLAN is required. First, we verify the current VLAN table to confirm that VLAN 40 does not already exist on the switch. This avoids accidental duplication and confirms that a new VLAN needs to be created. Next, we enter global configuration mode and create the VLAN by using the VLAN keyword followed by the VLAN number. After the VLAN is created, we assign a descriptive name so it's easy to identify its purpose, and then exit VLAN configuration mode. Finally, we display the VLAN table again to verify the result. The output confirms that VLAN 40 now exists, is active, and appears with the correct name, indicating the VLAN was created successfully. Renaming a VLAN changes only the VLAN's label, not its VLAN number or function. Traffic continues without interruption. To rename a VLAN, the VLAN is accessed by specifying its number, and a new name is assigned. Depending on the VTP mode, this name change may stay local or propagate to other switches. Here, a VLAN already exists, but its name is incorrect. First, we verify the current VLAN name by displaying the VLAN table. This confirms that VLAN 20 exists and shows that its name is incorrect. Next, we enter configuration mode, access VLAN 20 by specifying its VLAN number, and assign the correct name. Renaming the VLAN updates only the label and does not affect traffic or port membership. Finally, we display the VLAN table again to confirm the change. The output shows VLAN 20 with the corrected name, verifying that the update was applied successfully. Deleting a VLAN removes it from the VLAN database and immediately affects any ports assigned to it. This is done by using the no VLAN command followed by the VLAN number. Default and reserved VLANs cannot be deleted. In VTP environments, deletions must be handled carefully since they may propagate. In this scenario, a VLAN is no longer needed. First, we verify that VLAN 30 exists by displaying the VLAN table. This confirms that the VLAN is present on the switch and identifies it as the one to be removed. Next, we enter configuration mode and delete the VLAN by specifying its VLAN number. Removing the VLAN deletes it from the VLAN database and immediately disassociates any ports that were assigned to it. Finally, we display the VLAN table again to confirm the result. The output shows that VLAN 30 no longer appears, verifying that the VLAN has been successfully removed from the switch. An access port carries traffic for a single VLAN and sends frames untagged. This makes access ports suitable for end devices such as PCs and printers. If an access port is assigned to the wrong VLAN, the connected device will be placed into the wrong broadcast domain, often resulting in connectivity issues. To assign a port to a VLAN, the interface is selected first. The port is set to access mode and then assigned to the required VLAN by specifying the VLAN number. The VLAN must already exist. Once applied, the connected device immediately becomes part of the new VLAN. Here, a PC connected to a switch port needs to be assigned into a specific VLAN. First, we verify the current VLAN assignment for interface FA0/5 by displaying the VLAN table. This confirms that the port is currently in the default VLAN and needs to be reassigned. Next, we enter configuration mode, select interface FA0/5, explicitly set it as an access port, and assign it to VLAN 40. Setting the port to access mode ensures it carries traffic for only one VLAN. Finally, we display the VLAN table again to confirm the change. The output shows interface FA0/5 now listed under VLAN 40, verifying that the port has been successfully reassigned. A voice VLAN allows an IP phone and a PC to share the same physical switch port. The port is configured as an access port for data traffic, and a separate voice VLAN is assigned for the phone. Voice traffic is tagged and prioritized, while data traffic remains untagged. Here, an IP phone and a PC share interface FA0/10. The PC should use VLAN 40 for data traffic, and the IP phone should use VLAN 50 for voice traffic. First, we create and name the two VLANs. VLAN 40 is used for data traffic, and VLAN 50 for voice traffic. Next, we configure the switch port as an access port, and assign the data VLAN to the PC, then set the voice VLAN for the IP phone. Finally, we verify the configuration by checking the switch port settings for interface FA0/10. The output confirms that VLAN 40 is used for data traffic and VLAN 50 is used for voice traffic, indicating the port is correctly configured. VLAN 1 is the default VLAN on Cisco switches and is used by several control protocols. For security reasons, user devices should not remain in VLAN 1. Best practice is to move active ports to another VLAN and shut down unused ports. In this example, we want to remove an active port from VLAN 1 and make sure any unused VLAN 1 ports are shut down to improve security. First, we identify which interfaces are still assigned to VLAN 1 by displaying the VLAN table. This shows us which ports are actively in use and which ones are no longer needed. Next, we enter configuration mode and select the active port that should remain in service. The port is confirmed to be in access mode and then reassigned to VLAN 40, removing it from VLAN 1. After that, the unused ports are selected as a range and administratively shut down to prevent unauthorized access. Finally, we display the VLAN table again to confirm the changes. The output shows the active port now assigned to VLAN 40 and the unused ports no longer active, confirming that VLAN 1 is no longer used for end devices. Inter-VLAN routing allows devices in different VLANs and IP subnets to communicate by using a Layer 3 device, while still keeping VLANs logically separated and broadcast traffic contained. The reason we need inter-VLAN routing is that VLANs create separate Layer 2 broadcast domains and IP subnets. Devices in different VLANs cannot talk to each other using switching alone, so a Layer 3 gateway is required to move traffic between them. This approach allows controlled communication where it's needed, without breaking segmentation, while also improving security, scalability, and overall network design flexibility. There are 3 common ways to implement inter-VLAN routing. In this session, we focus on the first option, using a router with multiple physical interfaces, where each VLAN connects to its own router interface. We'll cover the other 2 approaches, router on a stick and Layer 3 switching in the next section when covering trunk ports. This inter-VLAN routing method uses a separate physical router interface for each VLAN. Each router interface connects to a switch access port that belongs to a single VLAN. That router interface is assigned an IP address, which becomes the default gateway for devices in that VLAN. Because each interface connects to only one VLAN, there is no need for trunking or VLAN tagging, which makes the design very simple and easy to understand. However, this simplicity comes at a cost. Every additional VLAN requires another physical router interface and switch port. As a result, this method does not scale well and is mainly used in labs or very small networks. In this example, 2 VLANs need to communicate, and each VLAN uses its own router interface. First, each switch port connected to the router is configured as an access port and placed into the correct VLAN. Next, each physical router interface is assigned an IP address that matches the VLAN subnet. This IP address becomes the default gateway for devices in that VLAN. The router interfaces are then enabled so they can forward traffic. Once both interfaces are active, the router can route traffic between the VLANs because it has a directly connected interface in each subnet. Verification confirms that devices in different VLANs can now communicate. Alright, let's quickly wrap up the key ideas from this section. VLANs are used to logically divide a Layer 2 network into separate broadcast domains. By containing broadcast traffic within each VLAN, overall network performance improves and traffic is easier to control. VLAN information is stored separately in the VLAN database, which is why VLANs can still exist even after clearing the startup configuration. VTP determines whether VLAN changes are shared across switches or kept local, and an incorrect VTP configuration can impact multiple devices at once. VLANs are also divided into different ranges, including normal, extended, and reserved VLANs, with VLAN 1 and other reserved VLANs not intended for end-user traffic. After VLANs are created, ports are assigned using access or voice configurations, and unused ports should be shut down for security. Because VLANs isolate traffic by design, communication between VLANs requires Layer 3 routing, which can be implemented using routers or, more commonly, Layer 3 switches using SVIs. Next, we'll move into inter-switch connectivity. This is where we focus on how switches communicate with each other using trunk links. We'll look at 802.1 queue tagging, native VLAN behavior, allowed VLAN lists, and common trunk misconfigurations. These topics tie directly into what you've already learned about VLANs and are essential for building scalable, multi-switch networks. Before moving on, take a quiz to test your understanding. Quizzes, summaries, and slides are available on ccna.academy. If you have any questions, leave a comment below and I'll be happy to help.